Salía rapidito, sí, salía rapidito. Sí, eso yo bajó de la integral, empezó a bajar.
بسم الله الرحمن الرحيم الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to the 6th class of the course. Today, inshallah, we're going to be starting topic number 2. So we're done with topic number 1. Topic number 1 was on the mathematical foundation. I see some people smiling. Okay, I think that's the spirit of everyone. So this is an experiment that, okay, so the outcome is your feedback, whether we should actually remove the first part or not. Okay, my opinion is no. Okay, because you're going to see that starting today, and this is actually what we're going to be doing for the rest of the course. Everything will be matrix multiplication. Okay, but now you see, okay, matrices are just some numbers put together, and there's always some mathematical object that's behind them. And you're going to see, okay, starting from, okay, when we start with the application part, which is like robotics, of all of the differential geometric terms we were taking, you're going to see, you're going to appreciate that if you know what the background, okay, what this object represents abstractly, then you're going to be understanding this weird operation that will be happening and all of these weird expressions that will in the end be just matrix multiplications. Okay, so this is the idea of the first part, and this is the motivation. So again, so you experience it as beginners in this topic, whether it's useful actually to have this background on differential geometry, which is, by the way, we've only had one lecture on differential geometry and not two lectures on vector space, so which is abstract linear algebra, one lecture on group theory and one lecture on basic set theory. So we've only had one differential geometry background. Okay, if you really want to understand differential geometry properly, I would say you need 5 credit hours course. Okay? That's only on differential geometry abstractly. Okay, but all of this torturing stuff. So the application part, which is what we're interested in the course, is the robotics. Robots or robotic mechanisms, unless otherwise stated, we assume that they are just rigid bodies connected together through joints, and that's it. So any, okay, I will not say any, but the majority of the stuff that we're interested in, so that includes humanoid robots, that includes multi-rotary UAVs with, okay, even if the propellers are moving all over the place and they are variable tilting, then we can model them with rigid bodies connected together through joints. If you understand properly how to model rigid bodies and how to interconnect rigid bodies using these joints, you have a very powerful tool that you can implement in different fields. Okay, independent of where this robot moves, whether underwater, in the air, okay, on ground, this is irrelevant of how we understand the dynamic model of the robot itself. This is the point of the course where you can start working on the course project. So the first thing you do at the course project, you choose a team. I'm going to send, of course, the precise instructions later on, but the team, okay, I would say out of 4 or 5, so that because we have a large number of students. So later on, there will be a presentation day. So we're going to have 2 days for presentation for the final presentation. And also it will be easier to follow up in that sense. So choose a team of 4 or 5, okay, minimum 3. That would be really the absolute minimum. But I would say 4 or 5 is good. Choose a robot that you're interested in. The robot has to be, this is the main, okay, like constraint on the robot itself. It has to be modeled by number of rigid bodies connected to each other. So that's the second thing. So if you have a robot in mind, that would be okay. If you don't, I'm going to post some options or some inspiration ideas that you can use for your project. And then what you're going to be doing is modeling it, so representing it mathematically on paper. Large part will be mathematically. You have to write this mathematics, so there will be a lot of reporting and writing all of this math down with the tools that we're going to be using. Okay, so this is an application for the tools that we're learning here in the course. Then after that, so the basic thing, the least thing to do in a project is just to model all of the dynamic interaction between the different links of the robot you have, and to see it whether in any simulation tool, whether in MATLAB or in Gazebo, if you want to do something more fancy. The next step is to do, so that's the basic level. The next level is to do some motion control, to have this robot moving in a way that you that you want. And the third thing is to have interaction control, is that to take this robot and to hit something on the wall or to write or to do or to interact physically with the environment. So these are the three levels that you choose which you want to target, depending on, of course, on the team that you form. So again, and more on that later for the detailed instructions. What the approach, so the tools, when I say tools that we're learning in the course, I mean here the Lie group approach for describing rigid body kinematics and dynamics. First, let's just do a little bit of survey. Who here has experience with modeling rigid bodies? Had a course on rigid body modeling, okay? Jacobians, forward kinematics, inverse kinematics, okay, everyone. If I give you one rigid body alone, how do you represent this configuration? What? Okay, specify a frame, put some frame fixed on the ground, put some frame fixed on the body. How do you describe this relative orientation and position of the draw, or sorry, of the body? Transformation matrices, okay. Who here is familiar with transformation matrices, homogeneous matrices? Okay, very good. So just 4x4 matrices that has some, okay, very good. Who here is familiar with Euler angles or how likes them? Okay, very bad. Okay, we don't like them. Okay, that's good. Okay, so you're familiar with them and you don't like them. That's okay. We're not going to be using Euler angles because Euler angles is a chart for the manifold of the configuration space, as we're going to be seeing. Who here is familiar with quaternions? Little bit. Do you understand it? A little bit. Okay, we're not going to be dealing with quaternions. So we're not going to be using Euler angles. We're not going to be using quaternions for representing orientation. We will be using homogeneous transformations. But again, instead of and this could have been the starting point, and it's actually the starting point of some of the famous textbooks, that the first thing is that we have homogeneous transformations. Let's start talking about robotics. That's not what the approach we're going to be doing. We're going to be building it, connecting this abstract notions that we introduced earlier in differential geometry to this, and motivate why SE3 or why homogeneous transformations are a good representation for representing the configuration of a rigid body. So we're going to be deductively, okay, deriving this notion. SE3 is called the special Euclidean group, and this is the configuration space of one rigid body. Everything we're going to be doing in topic number 2 will be for one rigid body. Topic number 3, we're going to be starting to have more of these rigid bodies and connecting them through joints and so on. If you understand what SE3 is and you understand what homogeneous transformations really are, not just to matrix manipulation or to do some mathematical tricks, if you really understand what it is, you have a very good background in dealing with, again, as I said, a large number of robotic systems in general. And I quote here Selig, that says that this group, which is SE3, is the most important one for robotics. And as I mentioned here, we're going to be starting not from numbers, because starting from numbers, this is you immediately start thinking in terms of a chart or in terms of coordinates. We're going to be starting abstractly. So when we say coordinate-free description, we're going to be talking first abstractly. What do we mean by configuration of a rigid body? Then we're going to be starting giving all of the assumptions that you need to put so that you can have numbers. And the numbers, all of the math that we're going to be doing with numbers will not exceed matrix multiplication, okay, by matrices by themselves, matrix by matrix multiplication, or matrix by vector multiplication. That's it. Let's start with the configuration space of a rigid body. Some abstract notions. So these are abstract concepts that we're going to try to clear out. You should be differentiate between what a Euclidean space is, n dimension, and n here, whenever I say n, this means that this holds for 2D, okay, which are rigid body in a plane, which is what we use, for example, if you want to describe mobile robots that move on the ground. So this is usually, you don't assume there's any height, it's just something that lives on the plane. So this is for the case n equal 2, and the general case is 3D, so n equal 3. So differentiate between n-dimension Euclidean space, what a rigid body is, and what a coordinate frame is. Let's start with the first one. An n-dimension Euclidean space is the following. It's an abstraction of the physical space we are living in. So this is Euclidean space, what we're living in, abstractly. There are two types of information that are existing in this abstract space, something called points and something called free vectors, okay? So this here is a point in Euclidean space, and this is another point. It's a point. It's an infinitesimal point in free space. Sorry, in the Euclidean space. And there are also stuff called free vectors. So this is a free vector, which is what we, okay, like in natural language, we say it's a direction, right? So this is a direction. If I tell you how to go to building 22, you tell me go in this way. So you see, we're talking about directions. You don't have to connect 2 points to tell me, okay, go from this point to that point. This already has a meaning, this direction. So this direction has a meaning, this direction has a meaning, this direction has a meaning. We need to provide some abstract notions to start to do, again, so to start to give this Euclidean space some structure to start working with it. One of the things that we give it is to make it into a metric space and give it something called the metric. The metric is simply a map that would take 2 points in this Euclidean space and give you some positive real number. And it measures the distance between any 2 points. Okay? So the distance between any 2 points is a well-known concept. It's just an assumption that we assume that we can do it given this space. And this is not general, by the way. So you don't think that you can measure the distance between any 2 points on any manifold or on any space. For example, if I give you the surface of the Earth and I ask you what's the distance, okay, between Paris and between Dhahran, what is it? Not defined, right? So that's an example of something that does not have this notion of a metric space, or you cannot calculate the distance between 2 points. Even though Paris is a point on the surface S2 and Dhahran is a point on the surface S2. So you can have 2 points and you cannot be able to calculate the distance, but Euclidean space that we're living in, this notion is well defined. I can calculate the distance between 2 points. And there's also another way, whether I can, if I give you free vectors, whether you can say it's right-handed or left-handed, okay? So I can say whether these 3 together make a right-handed frame or a left-handed frame, or they are together, they are right-handed or left-handed, okay? I can do that also in Euclidean space. That's an abstract notion, no numbers yet. The second thing is a rigid body. What is a rigid body? So let's say that this is a rigid body here, okay? How do you abstractly define it? It's a subset of Euclidean space. So you need two kinds of information. You need to tell me the subset, how many, like which part of space does it cover? Okay, so you see, for example, it has this shape, it covers all of these points. How many points live in this subset? Infinite, right? You have an infinite number of particles all rigidly connected to each other. This is what makes a rigid body. And because they are rigid, right, a distance between any 2 points here does not change, right? So this is where you use the distance metric. And you also have, for any rigid body abstractly, the notion of a mass density function. If I give you any point here, you can tell me what its density is. Okay, now if I give you a bunch of points, if I give you all of the points on the rigid body, you can have this notion of mass density. Of course, you can, the most basic idea is to think of the mass density function as constant, right? And then all of this rigid body has one mass in the end, right? And this mass represents like the integration of this constant function over all points here. So this is just an abstract notion, but this will be very helpful. The density function, we're not going to be using it this far in the kinematics. It will appear later in the dynamics. The third thing is coordinate frames. So everything we said about rigid bodies and about Euclidean space that you see here in this illustration is general, is abstract. You start giving them numbers by using what's known as a coordinate frame. So the coordinate frame consists of 4 things. It's a 4-tuple. First, it's a special point in the Euclidean space. We call it the origin of the frame. And 3 linearly independent orthonormal free vectors. Okay, we know what free vectors are, so they are directions, and they need to be, for them to make a coordinate frame, they need to be linearly independent and they need to be orthonormal. So this means that we need to be able to judge actually whether they are orthonormal or not. So we need this extra structure of Euclidean space. Now, if I give you this frame and I give you an abstract point, so for example, this is the frame. Let's choose that this frame that we have here in the room is this corner. So you see it's a specific point in the Euclidean space. It's the corner of the room. And let's assume that we have 3 V vectors that we chose to be part of our frame, of the room frame. One of them is this direction, one of them is that direction, one of them is this direction, okay, which make up this frame. If I give you the frame and I ask you now about can you represent a point in the Euclidean space? You can tell me yes. I can give you 3 numbers, okay, in general, in 3D, of course. three numbers, P1, P2, P3, which are like the projection of this point in this direction, the projection in that direction, and projection in this direction. The same also for a free vector. So a free vector itself, I can also project it into these three directions and get three numbers. And here, so P index up, E hat index down, there's a summation convention, right? The Einstein summation convention, okay? So this is P1 multiplied by E1 hat plus P2 multiplied by E2 hat, and so etc. until n dimension. This is abstract, and this is all what you just said about. First thing I start with is choosing a frame. Okay. What is a Euclidean system in 2D? The Euclidean system is simply a bunch of these Euclidean spaces, all of them overlapping with each other. So you can have a rigid body that corresponds to your robot. Again, it can be one rigid body or can be multiple rigid bodies connected to each other. But this is just an example of one rigid body. The environment itself that this robot is interacting with can be another rigid body. You can also have observers. You can have a Euclidean space where you want to look at the rest of the world. It can be, for example, the room itself. The room itself, even if it doesn't have any matter inside, I can move freely inside of it. It's still a Euclidean space separately from the others. And also, for example, if you have a camera, if you have a sensor, if you have a motion capture system that's doesn't have any, it's not a rigid body, you just want to observe stuff in this Euclidean system, this is considered to be an observer. The term pose, are you familiar with the term pose? P-O-S-E? Okay, so you're familiar with position, orientation, both of them combined is called the pose. So when we say the pose of a rigid body, we mean the combines, just one word to say rotation and translation, sorry, orientation and displacement at the same time, position and orientation. If I give you two rigid bodies, this rigid body and that rigid body, so a rigid body that lives in Euclidean space I and another rigid body that lives in Euclidean space J, can you describe the relative pose between them? Yeah, makes sense. Abstractly, it makes sense. Even without any numbers, I can still represent, I can talk about this is moving with respect to that, or this is a relative orientation. So for example, here, they both have the same orientation, right? And the same position. Here, they don't have the same position. Like that, they don't have the same orientation and so on, okay? So I can abstractly talk about this map. So this map, which represents the relative pose between two Euclidean spaces, is denoted by Hij. The space of all relative poses will be denoted by SEIJ. Okay, so all of the possible configurations or relative configurations that these two Euclidean spaces can have is denoted by this SEIJ. It doesn't have a name yet. Okay, it doesn't have a name yet. We're not giving it any names. This is just an abstract space of all possible relative poses. If I ask you, what is the configuration of the rigid body? Can you answer that question? So what is the configuration of this rigid body? What is it? What is it? Is it even defined? In other words, what's my position? Relative to what? You see, you always need some relativity. Right? You need to always say position of something with respect to something, or displacement of something with respect to something. What is the position of Dahran? Doesn't make any sense. Relative, for example, to someplace else, now we can start talking about. What is the position of Earth by itself in space? Doesn't mean anything. With respect to the sun makes sense. What's the position of the sun by itself doesn't mean anything. The position of the sun with respect to its neighboring galaxies and blah, blah, blah makes sense. So you always need this notion of relative poses. You cannot talk about a pose of something by itself, abstractly. But usually when I say, and this is an assumption, when I say the pose of a rigid body, I always have implicitly some home position, right? So if we're a bunch of robots here in the room and we're going to start moving around, we need to all agree that there's one location in this room where this is the home position, okay? This is the zero, it's like the origin in terms of position and the origin in terms of orientation. So we all need to agree on that. This is known as the reference pose. And when we're doing robotics, you always assume you have this reference pose one way or another. Now let's start to giving them numbers. If I choose some coordinate frame, so these new red frames, Each coordinate, each Euclidean space will have a coordinate frame of itself. By the way, the coordinate frame does not need to be fixed on the rigid body. It can be even outside of the rigid body in general. Okay, and everything we're talking about will still work. That's why we have this notion of Euclidean space. So the most important thing is that it's associated to the Euclidean space. So if the Euclidean space rotates or the Euclidean space translates, this frame moves with it. With these frames, psi1, psi2, and psi3 up to psi, okay, depending on how many rigid bodies you're talking about or how many Euclidean spaces you're talking about, instead of working with abstract concepts, we can start to talk about maps. Okay? The maps that we're going to be talking about, so these abstract Euclidean spaces, they are like a manifold. And these reference frames, we start to talk about charts. We choose a chart that represents this manifold. And whatever maps that we have in here, they make sense because they are maps from Rn to Rn. And we know how to do Rn stuff, okay? Vector multiplication and matrix multiplication and so on, okay? So we know how to deal with Rn. Abstractly, we cannot do that. And this is the notion of, this is the starting point, is that always start with frames. But don't forget that if anything you do with calculating these frames should be, you should always map them back to the abstract notions, okay? So if you have something that appears in one frame, but not in another, there's something wrong. So keep that in mind. So let's now look at these transformations. So these maps that go from Rn to Rn, which would represent, okay, this relative pose between two rigid bodies or between two Euclidean spaces. If it's a rigid body transformation, if we require it mathematically to be a rigid body transformation, we should make sure that it preserves distances. Okay. In other words, if I tell you that I have this rigid body and it's moving in this direction, okay, so it's being translated. This action that acts on Rn and takes you to Rn. Okay, this map, this linear map that will take you from Rn to Rn. It should preserve the distances. If I take any two distances before the translation and I check the distance of these same 2 points after the translation, they should be the same. Right? How do we measure distances in Euclidean space in Rn? With the norm, right? So the norm, so what this equation says is that if I take the distance, okay, if I take the difference between two vectors, okay, before the action of this map, and I take the difference after the action of the map, the distance should be the same. Make sense? Okay. How many ways, how many transformations fit this definition? Okay. First of all, this definition, a map that will satisfy this on Rn has the name of an isometry. Okay. Isometry, and you say that this is an isometric transformation. There are three ways that you can have these isometric transformations or isometric maps between Rn. One of them is translation, okay? Another one is rotation, and the third one is reflection, okay? So if I give you, it's hard to do reflection because I'm not a magician, but let's say reflection is when you look at a mirror, okay? So when you stand in front of the mirror and you take a frame, you're gonna see that if you had it right-handed in the mirror, it would be left-handed, okay? If you have a body, okay, that you're holding in your hand, this is a transformation that preserves the distances. So the reflection does not change the distances, but it changes the orientation of this Euclidean space. In general, and this is something I'm not going to be proving, but again, it's something that's known from linear algebra, is that isometries can always be written like this. So if I remember that phi h, okay, is an isometry from Rn to Rn. So if it eats a vector, okay, then this is equivalent to some matrix multiplication by this vector. That has, of course, this matrix multiplication has the same dimension as the vector, plus some offset, some translation part. Does anyone remember what we called this map? An affine map, exactly. So this is an affine map. This M should be, first of all, invertible, right? Because if I do the transformation, I can always go back, right? And I should get the same value, right? I should get the same vector or the same point. So, but not only that, for this transformation to be an isometry of Rn, M should be orthogonal it should be an orthogonal matrix, and psi should be any vector. So psi can be any vector. There are no restrictions on psi. So I can, okay, it represents a translation part, while M represents the rotation and the reflection. The set of all matrices, all n by n matrices that satisfy, that are orthogonal, they should satisfy this condition. Of course, this sounds familiar from the assignment that you should all have submitted by now. So this is called the orthogonal group, okay? It's a set, okay? So this is its definition, and it's a matrices, it's an n by n matrix. And we can always, if we have an n by n matrix, we can always try out. When we multiply two n by n matrices, we can get an n by n matrix. But the question is, if we multiply two orthogonal matrices together by matrix multiplication, do we get another orthogonal matrix? In general, yes. And you can prove it. Okay? This is part of the homework, next homework, inshallah. So this set has a group structure, and the group operation that would take two elements of it and give you another element in the same group is the matrix multiplication. Okay? But there's a problem here that an element of this orthogonal group can have a determinant that's either 1 or -1. That's also a proof for that will be in the homework, okay? This condition here, okay, implies that the determinant can be either of M, can be either +1 or -1. And we said that the determinant of +1 represents a rotation, represents that I take a rigid body and rotate it, okay? Of course, rotation means the point is fixed, so I'm like rotating around like this, so I'm not translating. Or I can do reflection. If I have robots moving around, have you ever seen a robot that reflects rigid bodies? So is this something physical? This is not part of what the Euclidean space we're living in. There's no reflections. So we want to rule out these reflections. So what we can do is that instead of looking at the orthogonal group of n, we can add one condition, and we're going to look at all of the matrices or all of the elements of the orthogonal group that have the determinant exactly equal to 1. So we're going to just rule out everything that has the determinant of -1. And this is called the special orthogonal group. Okay, so this is called the special orthogonal group, and elements of this special orthogonal group are called rotation matrices. Okay? So they are called rotation matrices because they rotate vectors in Rn. So they are maps from Rn to Rn. Okay? And they rotate, if I act by this rotation matrix on any vector, the result will be a rotation. In which direction, of course, depends on the R itself. But always it will be a rotation. It will not change the length of this vector. It will not translate it. It will only rotate it around some point. Clear so far? Okay. Any questions before we move on? Okay, you're very quiet. So you're either understanding everything or not understanding anything. Okay, time will tell. The special Euclidean group. Okay, the special Euclidean group. Okay, let's go back. Okay, sorry. One thing. So for these isometries to represent rigid body transformations, okay, then this rotation, this matrix should be part of SO3, and I have this translation part. So if I give you any isometry, you can represent it or identify it with one rotation matrix and one translation vector. And thus, this combination, so if I take the product space or I take the product set of these two together, then I can identify any isometry that would represent rigid body transformation by these two elements. One of them is a rotation matrix that lives in SON. The other one is a translation part. And here, if this isometry was relating or was describing the relative pose between some Euclidean space I and some Euclidean space J, then the rotation matrix would represent the relative orientation between this frame and that frame, and this translation would represent the relative displacement between these two frames. Okay. The product of these two spaces is what people call the special Euclidean group. Okay, so it's the product of them. So as a set, if I tell you what is SEN, you tell me it's just a pair of two things. So an element of SEN is a pair. The first element is something that lives in SON. The second element is something that lives in Rn. Everyone agrees? Okay. Let's see, what else? Okay, before scaring you, let's start. SEN, does it have a vector space structure? Or is it just a set? Or is it a manifold? You remember what we discussed, right? So we need to start working with it. Let's start even without talking about dynamics, without anything that's moving. We don't want to do analysis. So what we did before. Does it have a group structure? Let's even start before. SON, does it have a group structure? Why? Because you just proved it, okay? You already proved that. But again, and by the way, it's not a must. What I just mentioned here is that the group of orthogonal matrices has a group structure. If I restrict to a subgroup of it, a subspace of it, if it's a group or not, it's not always necessary. Okay, it's a fact, and that's something you can prove, that if I take rotation matrices that have determinant of 1, and I take the multiplication or the group operation of 2 rotation matrices, I get a rotation matrix. Okay, so if I have something that has the determinant of 1 and multiplied by another matrix that has the determinant of 1, the result has the determinant of 1. Okay, and this is because of a famous property. I don't know if you remember or not in linear algebra, that the determinant of the product of 2 matrices A, B is equal to the determinant of A multiplied by the determinant of B. Okay, so this is what you use for the proof. So now we have one group. Rn with the plus operation, so the vector addition, is it a group? Of course it's a group, right? You have the 0 vector, right? So this causes the identity of this group. I can translate like in one direction. I can add, I can subtract. It actually has a vector space structure, so it's even higher than a group. And if you remember, one of the axioms of having a vector space structure is that the set, and the vector addition, they should be an abelian group. So it is an abelian group. Is SON an abelian group? No, it's not. So SON is a group, but it's not an abelian group. Rn is a group, but it's abelian. This one has its own operation, which is the plus, the vector addition. This one has its own operation, which is the matrix multiplication. Everything sounds familiar? Okay, good. When I multiply them together, do I get another group or not? Trivially, you can always take any 2 groups and make them into another group, and this is called the direct product of 2 groups. This is trivial, and you're going to see an example in the homework, inshallah. Okay? So this is something that's trivial. You can always do that. If I give you 2 groups, you can always make them into a product group. Yes. That's a good point. I have to check. I think you can. If each one of them had a vector space structure, and you take the product, I think you can make it in a vector space. I don't see anything why would make it not. But let me check and come back to you. Okay. But as a group, okay, we can make them into a direct group. But you remember now, and this is something very deep. We said that SEN comes from isometries, right? So if I take these together and make them into a direct group, will the result correspond to an isometry or not? I need to check, right? So in other words, if I take these 2 together and then I get something that does not correspond to an isometry, then I don't have this product group. And that's actually the case. And this is part of what you're going to be proving in the assignment. Okay, in the homework, you're going to have a step-by-step, like you're going to be solving sub-problems so that you can prove this. Okay, this detailed construction. Okay, at your own pace. What this says is the following: that the special Euclidean group, it's a group. Okay, I can make it into a group, but it's a very funny-looking group. It's a group operation. We're going to be representing it by square. Okay, so the square. So again, first of all, what is the SEN? SEN is a pair of R and psi. The pair of them together I can call small h, and such that R lives in SON and psi lives in Rn. Okay, so if I have this is the set, but I still need to define the group operation. The operation that would take an element of SEN and an element of SEN and sends you to SEN looks like this. What it does is the following. If I take 2 elements of SEN, H1 and H2, H1 is equivalent to R1 and psi1, H2 is equivalent to R2 psi2, then then the result of taking the group operation of SEN between these two elements will give me the matrix multiplication of R1 and R2 in this order. And R2 will be multiplied by psi1, and we're going to have an addition of psi2. Do we have an identity element on this group? Yes. The identity element is the identity element of SON and the identity element of Rn. So the identity element of Rn is the zero vector. The identity element of SON is just the identity matrix, right? It's something that if you multiply it by a vector, it does not rotate, it does not change it. So this is what the identity element does. The inverse element. How do we define the inverse element? Does anyone remember? If I give you any H, how do you define its inverse? Exactly. When I take the group operation of this element with H, they have to yield what? The result has to be the identity element. So it's also a homework for you to show that this is actually the inverse element for any H. So if I give you some R and some psi that correspond to an isometry, and I tell you what's the inverse of this isometry, what will happen is that the rotation matrix will be transposed, and the translation part will have a mixing of the rotation part minus the rotation part transposed multiplied by the original translation that you had. This operation, so this kind of operation is called, means something very deep. It means that SEN is isomorphic to this product as sets but not as groups. So it's not the product of two groups. It's not the direct product of two groups. It's something that's called the semi-direct product of two groups. Who saw here this term before? Semi-direct product of two groups. Anyone saw this symbol before in the definition of SEN? Okay, so this is something new. So what I mean, what is meant by this notation is simply that SEN is a group and it's made up of two groups, but when we combine these two groups, we don't combine them in a trivial way. Okay, we combine them in a way that actually like couples them together. This is very deep. The reason is the following. Usually when you start by introduced to dynamics or in kinematics in like in general, you start by talking about a point mass, right? So you say, I have a point mass, I know how to describe its motion. Can I have Newton's second law that says the rate of change of the momentum is equal to the force applied to this point mass. Okay, then you forget about translation. You go to rotations. You say, okay, I want to describe rotations. You don't know how to do matrices. If you're still undergrad, then you get introduced to what? Euler angles, right? Or at least you start even in 2D first. You say, I want to understand rotations in 2D. How do we describe rotations in 2D? By just one angle, theta, right? By just some heading, right? Just one number it's good enough. But this number by itself doesn't even have an R structure, right? It's not a real number. It's something that goes from minus pi to pi. It's an S1. It's a circle. So you see from the very basic, even if you talk about rotations in 2D, you have a manifold structure. But again, you can always do tricks by saying, okay, I'm going to represent it from minus pi to pi. And if I go to pi, I'm going to shift and go back to the other side, and you start having all of these discontinuities. Okay, but again, what you're actually doing is that you're taking the circle and you're just putting it into a straight line. So this is using a chart for R, or using a chart for the circle, whatever that means. But now when you start to combining the translation part with the rotation part, this is where it becomes very tricky. Because if you start understanding angles in 2D, then, okay, the natural thing is, okay, when we go to 3D translation, instead of looking at a 2D vector, we go to a 3D vector, easy. When we go to 3D rotations, what happens? Three angles, very big, very big mistake. Why?
Because you have a lot of ways to describe this.
Very good point. I can choose, there are actually 24 ways to describe three angles for one rotation matrix. Okay, the 24 actually are, so they're actually, you can divide them into two sets, 12 and 12, and both of them are equal. Okay, so you can give me three. So for example, roll, pitch, and yaw, all familiar? Okay, so how do you rotate them? You rotate around the X and then the Y and then the Z, or the Z and the Y and the X. Which one? It depends. You see, so don't confuse yourself. Forget about all of this stuff. Okay, Quaternions was a one way to get around all of this, okay? But quaternions have a problem of their own. I'm going to mention it maybe later. But you see what we did here is that we started by imposing what do we need to describe rigid bodies, and then it follows naturally that SEN is the configuration space. Okay? We did not start by translations and rotations, then we made them up. Because even if you had translations and rotations, when you combine them, it's not trivial. And this, okay, expressions, they don't make sense unless you look at them from the isometry point of view. And this will be your homework. Okay, so you're going to prove that really SEN has this structure, has this group operation, has this inverse when you look at them, because they represent isometries that come from Rn to Rn, and these isometries are a mathematical representation of these abstract concepts as relative poses between two Euclidean spaces. Having all of that said, okay, Ziad, I have a question.
Does it mean SEN now is not an isometry?
Sorry?
Does it mean now, like, what does it represent as SEN after combining both? Now it's not isometry.
It's not, okay, I see your point. So if you take an element of SEN like this, and it represents as an isometry, then everything works. Then it represents a rigid body transformation. Okay. If you take rotation matrices and vectors and you combine them in a way that's not like that, then it does not represent, okay, rigid body transformations. And this actually has been like some references had this like this struggle, or okay, is it a direct, do we combine these two by a direct group, or do we combine them by a semi-direct group? And the answer here that you're going to be showing, okay, you're going to proving yourself, it is definitely a semi-direct group. You cannot have a direct product. This also means something very important. If you're designing, if you want to describe rigid body transformations, okay, or describe rigid bodies, can we separate rotations and translations?
In order we were doing this.
Exactly. Can you do that in general? By this construction, no. Okay. You see, rotations and translations, they are coupled together. Okay. You cannot talk about translations and rotations separately. Similarly, if you're designing a controller for this dynamical system, do you design a controller for rotations and then a controller for translations and combine both, or do you do them both together? What this says is that you should treat them both together. You should describe them mathematically together. You should analyze them together. You should describe, if you're going to do controllers, if you're going to do state estimators, if you're going to do whatever, okay, and applications, you should do them both together. Okay. So this is the motivation. Now let's look at what are homogeneous transformations, what you're all familiar with. Homogeneous transformations can be thought of as a trick, okay, but they actually have a much deeper abstract, okay, knowledge it's way beyond what we're not going to be covering at all, and it's I can point you some references if you're interested, but this is something called projective geometry. Okay, rotations and translations, you saw they're coupled together. Okay, so if I want to do rigid body transformations, I need to do first rotations, and then I do both at the same time, rotations and translations, with these funny operations that I had. So I always talk about these coupled. There is a nice way using projective geometry that we can go up one space. So we're talking about Euclidean space. We're talking about 3 dimensions here, or n dimensions. If you can go up one space using these ideas of projective geometry, we can represent SEN, an element of SEN, which is the pair of R and psi, by some matrix that lives in the higher dimension. So if this is a 3-dimensional rotation matrix and this is a 3-dimensional vector, I can go to 4 dimensions and I have a matrix representation that's very nice to work with. And then when I have this matrix representation, which is, by the way, called the homogeneous representation of H, then the operation that I had between 2 isometries, okay, or between 2 elements of SEN, I can do them very simply by matrix multiplication. You see, these are exactly the stuff that we had before when I compose 2 elements of SEN. And when I take the inverse of this 4x4 matrix, I simply get this construction, which was also related to what we had before. Okay. But now you remember we said that actions of SO3 and actions of isometries, they are actions on Rn. And now I went to a higher dimension. So how can we solve that problem? We also take vectors. So the action that we had of SCE on Rn, we also can represent them as actions of these homogeneous transformations on n+1. So usually what we do is simply, I'm pretty sure you've been taught it as a trick, that take this 3 vector and put it with the 1 down, and then everything will work out in this. So this was the affine map that we had and we started with as an action of SEN on Rn. And the vector V, which is this 4-dimensional or this n+1 dimensional version, which is this one, of the original n-dimensional vector that we started with, is called the homogeneous coordinates of V. Okay? So the word homogeneous comes from all of these concepts of projective geometry. Okay? So this is, again, what we're not describing here. But again, you can think of it as a trick, so that instead of working with pairs of stuff, you can do everything with matrix multiplications in 4 dimensions, or you can think of them actually that there is something deeper going behind that. Okay? But in the end, the calculations, they are the same. So that's the conclusion. So what is the configuration of a rigid body? So we introduced all of these different notions. We started abstractly. We said the abstract configuration of a rigid body does not make sense unless you choose this reference configuration. Then we can talk about abstract relative poses, okay, between any 2 Euclidean spaces. Each Euclidean space can have a rigid body or not, can be a rigid body or can be an empty set. Then we represented with numbers, okay, as stuff that act on Rn to Rn, so maps from Rn to Rn, linear maps from Rn to Rn. So sorry, not linear maps. They are affine maps from Rn to Rn. And they had the pair of rotation matrix and a translation vector. And then we said that we can take these with projective geometry and put them into an n+1 dimensional matrix, or an element of the general linear group in n+1, which we called homogeneous matrices. Okay? And all of that depends on the frames you put. When you do, shall I say this? Okay, well, I'm not gonna save the time. I'm not gonna say it because I don't confuse you. Any questions so far?
Have limitations, such as Euler angles that have some problems.
Very good question. Very good question. Let's go back here. And now you can appreciate this part, which is not coming, this one. We said that an element of SEN is identified with a map here. You know what identified means? What do we mean mathematically when we say that this is identified with that? That means they are 1-to-1. Okay, they are bijective. If I give you this, you give me that. If I give you this, you give me that. They are equivalent, right? Very simply, it's by this map here. You see, if I give you the m and the psi, okay, you know precisely what this map is. And if I tell you the map, you know precisely what the m and the psi is. Clear? Okay. So you see, it's well defined. They're 1-to-1. The problem of Euler angles is that they are only a chart. It's not a 1-to-1 representation like that. And this is where you have the singularities, they come place. Okay. Same with quaternions. Quaternions, they represent rotation matrices, not in a 1-to-1 map. They actually have they don't have a surjective map. Sorry, they don't have an injective map. Okay. So in other words, I can give you one rotation matrix and you can represent them by 2 quaternions. Okay. And usually they are opposite of one another. So they are not 1-to-1. The only thing that's 1-to-1 and has this nice structure is SEN. Okay. And it also has, more importantly, it has a very nice structure that we're going to be using later on. So this is also a big advantage. It's not just mathematically that's 1-to-1. They have a very, very rich structure. Okay. And this is what we're going to be using for all of the calculations and what we're going to be doing next. So very good question. Other? Hamad.
Slide where we talk about the tree.
Yeah.
Compared to the regular conditions where we have each as a tuple
Yeah.
of the rotation.
Yep. Yep.
The trick that we claim this is, doesn't that make, can't we, this expression itself as a matrix representing or containing the rotation matrix and the 0 and the 1, can it be thought of itself as a group?
It is a group. It is a group. So, and this is actually the general linear group, right? So this is the general linear group that, okay, in 4 dimensions. It's a 4-by-4 matrix. It has an inverse. Okay, and if it has an inverse, then its determinant is not equal to 0. So it's a general linear group. But it's not orthogonal. So this matrix is not orthogonal, right? It has an orthogonal component of it, but it itself is not orthogonal. And it does not have a vector space structure. You see, it is, so you're right, it is a group. And actually what we just defined here is a map between this group and that group. So this is a group of 4x4 matrices. And this is the group the funny group that we defined, right? Which had the square operation. And when you have a map between two group operations, okay? So between groups that respects its group operation, what did we call that? A group homomorphism, exactly. Which means that this group with its operation, which was this one, and that group with the matrix multiplication, which is its operation, are isomorphic as groups, right? So anything you can do with this, you can do with that. It's just a choice. You remember, this was something that we mentioned before. When you talk about you have two stuff that are isomorphic together as sets, as vector spaces, as groups, or as manifolds, this means anything you can do with that one, you don't lose any information when doing it from the other one. It's just a choice. So here, if you want to do everything as a tuple, it will work. If you want to do everything with matrix multiplications, it will also work. Okay. Of course, it's you're familiar, you're well trained to think about matrices and to do matrix multiplication. It's also good for, is it good for computers? Is this one better for computers, or is this one better for computers? This one is better for computers, right? Because I don't need any extra. If I have 100 rigid bodies and I have a 4x4 matrix, then I have, see how many zeros I'm going to put here and how many ones that are completely redundant. They're just for us to do matrix multiplication, right? But if I have a computer, this one is good. Okay. So you see, so this is how you think, right? They are equivalent. They are 1-to-1. Okay. Other questions?
Is matrix multiplication.
The square one, or the one with the SEN, or the one with the homogeneous matrices? This one. This is defined like this. You see?
This one is matrix multiplication, or linear matrix multiplication.
This is so if I give you a matrix and a vector, this is what this does. It takes one matrix and a vector here, and a matrix and a vector here, and then it takes the matrix multiplication between the two matrices, and then it takes the second matrix, multiplies it by the first vector plus the second vector. You see?
For the next slide, it's we figured out is matrix multiplication for this one.
That's right. Because of the fact of this idea, right?
It's restricted for the matrix multiplication. This operator.
The square operator that we defined on SEN that represents these rigid body transformations, these isometries, turns out to be, when we represent the R and the psi in this form as a subset of these general linear groups, turns out to be just matrix multiplication. Okay. So again, that's why I'm saying you can think of it as a trick, or you can think of it actually that we found a very nice isomorphism, okay, or a group isomorphism between the group that has matrix multiplication, right, which is the general linear group, in a higher space. It's not in the same space. There's no way you can do it with 3x3 matrices. Okay, there's no way. That's why you need to go in higher spaces. Okay, when we go into higher spaces, this worked out to be very nice. And that's why we're using it.
We're going for the higher space for abbreviation for the rotation and translation. For example, if I like to, after this rotation or after this transformation, I'd like to another transformation.
Very good point. Exactly. This is precisely what that says. Absolutely, you're right. And this is actually what the group operation says. So this is what this group operation says. So each one of these etches is a map that goes from Rn to Rn. So I might have this rigid body that was in this configuration, and then I did a transformation. It went to that configuration, and then I did another transformation that went to this configuration. So you see, I did 1 and then 2. So if I represent them as isometries, okay, which is what you have in the homework, you're gonna get that the corresponding R and the corresponding psi, they have to have this form. Okay. And the inverse has to have this form, because the inverse means that if I take the rigid body, transform it into this configuration, and then I go back, I should go to the same configuration I started with. Right? So this is what this says. Now, if you take all of these operations that come from the definition of the isometries and do them with this matrix multiplication, between matrices of this form, then it would work out very nicely. You're going to get the same result. And this is why it's an isomorphism. It respects the group structure. Clear? Other question, Hamid.
So, based on what you said now, expression of the group, so SE, and the translation we actually observe is actually a combination of translation and rotation.
That's right. That's right. Absolutely. That's correct. The translation that you see after two transformation, let's put it this way. So you see here, you see H1 was one translation. H2 was another translation. If I do H1 and then H2, the result that I got from going from H1 to H3, right? So let's assume that H1 went you from configuration 1 to configuration 2, and H2 take you from configuration 2 to configuration 3. Then H1 composed, which H2 would take you from 1 to 3 directly. Okay, and we're going to be working a lot with all of this stuff with proper indices later on. But that takes you from 1 to 3 is combining the translation part of it has rotation inside of it. That's correct. On that part, just so that at least because it's very relevant. If we didn't have this R2 here, we would have what? Psi1 plus Psi2. What would that be called? This would be called the direct product group. So this is what the direct product group, that I take I take rotations, I do the first rotation, and then I do the first configuration and the second configuration, then the result is the same as doing rotation, translation. That's it. The reason that the rotation and the translations are coupled is what makes this a semi-direct group, not a direct group. So continue your question. This one? Okay. This one? Which one?
Okay, going to the inverse.
The inverse?
So from here, we can see that moving from a particular point to another.
Applying an isometry.
Actually, perspective of the vector and the Rn aspect.
Okay, yeah.
Assuming, say for example, what we can see here is just from this point I'm going there, then
Okay, I see your point. Yeah.
But we can see that there's the rotation.
That's right.
So does it seems like as if locally it's translation, but zooming out we have some form of, we can't call it.
I say okay. I say so. The argument is the follows. I did rotation and translation, right? So I moved like that. The inverse should be what? I inverse the rotation, which is this part. The inverse of the rotation matrix is the transpose. Where does this come from? Comes from the fact of the orthogonal group. I think you proved it, right? Okay, so this comes already from that. The inverse of the rotation is the transpose. But what about this part? I translated. Why don't I get minus psi? Why don't I go back? This is again due to the fact of this isometry. It will be much clearer once we start putting indices, which is what we're going to be doing later on. The indices will make it much clearer. Okay, abstractly, this is the case. When we start putting indices, when we start looking at one frame with respect to the other, this will be clear. But keep it for now hanging. Okay, keep it for now. It's hard to get a head around. I agree, but keep it. For the same rotation, you can have multiple rotation matrices. No. The same rotation, for one rotation, you can have only one rotation matrix. It's always the case. That's the problem of the Euler angles. You see, representing the rotation matrix by 3 numbers or 3 angles, this is not unique. I can give you a number, I can give you 12 possibilities of 3 numbers that will give you the same rotation matrix. But if you have a rotation matrix, then it's 1-to-1 to the abstract rotation, the abstract orientation. It has to be. And this actually gives me a nice idea for a homework problem. Okay, so it will be in the homework. Okay. Okay, very good question. Do you need the angles? That's a very good point. If I want to design controllers, I need to know the angles. Okay. Hopefully by the end of the course, you'll see we don't need that. Okay. Good point. Yeah.
Regarding the last part, we said for Euler, we took a chart from the manifold, so it has some limitations, this chart.
Yes.
But when we began at first, we said that psi, in which we made the coordinates, are actually a chart from the manifold.
Yes.
So
yeah.
The problem of the bijection comes from the being that we took a chart in a different way, maybe, or it's not a chart problem.
The chart that we're talking about, there are different charts. The first chart is from the abstract Euclidean space to numbers by looking at the frame. The second one is having a chart for SO3 itself, which is the idea of not using a 3x3 matrix to represent this rotation by using only 3 numbers. And this is something we're going to be proving also in the homework, inshallah, that I have a 3x3 matrix representation of a rotation, right? Of orientation. How many degrees of freedom do I actually have in this 9 numbers, the 3x3 matrix? How many degrees of freedom? So in other words, if I give you any 3x3 matrix, but any 9 numbers, does it represent a rotation matrix? No. You need to make sure that the inverse is the transpose and the determinant is equal to +1. So all of these constraints, they reduce the 9 dimension of the matrix into 3 numbers. So in other words, SON is an n-dimensional manifold and Rn is an n-dimensional manifold. Okay. So this is 3 dimension, this is 3 dimension. Okay. What I said is not correct. In 3 dimensions, the dimension of SON is 3. The dimension of Rn is 3. So the dimension of SEN in 3 dimensions, and if you have a robot that's moving in 3D, is 6D, 6 dimensions. So you need 6 numbers locally, but globally not. In 2 dimensions, SON has the dimension of 1, and Rn has the dimension of 2. So you have 3 dimensions for the configuration space. And this is what you're all familiar with. If I have a robot that's moving in 2D, I need 3 numbers to represent it, X, Y, and heading. When you go to 3 dimensions, you say, okay, if I have X, Y, and heading, so it should be X, Y, and Z. And instead of 1 heading, I have 3 headings. They're all pitch yaw. And this is where everything breaks loose. Okay? We're not going to be doing that. We're going to be using a 9 numbers to represent the rotation. Okay, and it will make our life easier because it's 1-to-1. We don't have all of these singularities, all of these problems with parameterizations, with working in charts, and so on. Let's see if we have anything else. Okay, let's start by this one. And okay, we will not be finishing, but this is just a preparation for next time. So SEN is a group made up of the semi-direct product of 2 groups, SON and Rn. When we want to talk about the kinematics and the dynamics of rigid body, we want to talk about motions, it's not enough to talk about a group, right? What do we need in addition to a group? What is the structure that we need to talk about curves on this space and take differentiation and so on? A manifold structure, exactly. We need to make it into a manifold. SEN has a manifold structure. Okay. And this manifold structure, we need to impose some extra stuff that are already satisfied. So we don't need, you remember what I told you, remember last time, when we're talking about atlases and all of this stuff that abstractly, usually they are most of the time satisfied. So we don't need to prove that it's really a manifold. We're just starting by the assumption it is a manifold. And this is the reason of why, if you just want to have a feeling why this is true, is that the group operation between 2 elements of SEN and the inverse is smooth. So it's infinitely differentiable. And this is why we have it to be a smooth manifold. So it's a smooth manifold. So it's the best thing that we can have. It's infinitely differentiable. So we don't need to worry about any CK or any stuff. So everything we can differentiate as much as we want. And so SEN has the structure of a group and has a structure of a manifold at the same time, which makes it into what's known as a Lie group. SON was a subset of SEN as set. And it was also a subgroup of it when this was a group. Is it a manifold? When this is a manifold, the answer is yes. It is also a manifold. So if it's a subgroup and a submanifold, we call this a Lie subgroup. Okay. So the sub part means that if I start with only rotations, I keep on going, or I keep living in this small manifold. I don't go out of it. So this is just intuitively what it means. From next time, inshallah, this is our picture and what we're going to be working with, that rotations, change of rotations. If I have some, we're going to be working first with SO3, understand everything about it, and then we're going to move to SE3. You're going to see, because of this analogy, or because of all of these constructions, going from rotation to translation would be a piece of cake. Okay, inshallah. But again, this is the picture that we should be starting from next time, inshallah, where SO3 is a manifold. It's an abstract manifold. You cannot visualize it. It's a three-dimensional manifold, okay, in 3D. So I cannot plot it to you. It doesn't have a shape. It's very hard. And this shape in 2D, it becomes 1D, and it's actually very much similar to the circle. It's isomorphic to the circle, so it's trivial. So SO3 is a manifold, abstract manifold. If I have orientations that are changing, okay, I have rotations, this will correspond to curves on this manifold. If I have something that has a rate of change of the rotation matrix, so R dot, the rate of change of a matrix, we're going to be looking at it as a tangent vector in some tangent space. So there's a tangent space, there is a cotangent space. Everything will follow from there next time, inshallah. Okay. The same picture we're going to have for SE3. Abstractly, all of the calculations we'll be doing it will be matrix multiplication and vector addition, and that's it. Okay. Sorry for going over time. So that's it.